Hello, good morning. Can you all confirm if you can hear me clearly? Is everyone hearing me clearly?
We can hear you.
Okay, thank you so much. I want to welcome you to my lecture today. Of course, I'm having this lecture remotely because I'm a little bit under the weather. I'm going to return to in-person teaching tomorrow. We're starting in another topic today. And of course, we're going to have this topic today and tomorrow. We call it canonical correlation analysis. Okay, so in the outline, I'm actually going to walk you through the overview of canonical correlation. And of course, also going to talk about, the population definitions, the sample estimates, well, and that's also going to include the larger sample estimate. I'm going to talk about um, the uh, some basic measures, under this. Then I believe the focus tomorrow is going to be on looking into examples, okay, on this particular topic. So, by canonical correlations, I'm going to say, um, is a statistical method that we use, to exploit relationship between two set of multiple variables. Now, let me say this, or how this why we've been focusing on one set of variable. Okay, I'm going to say that again. We've been focusing on one set of variable, okay, whether in principal component analysis or whether in a factor analysis, it has been one set of variable, okay. But in canonical correlation, the focus is going to be on two set of variables, okay. And of course, we actually want to identify and quantify the association between these two set of variables. Okay. And the way we're gonna do that, we're gonna achieve that by finding linear combination of variables within each set that will maximize, their correlations, that I just talked about. So I'm gonna cite an example for you to be able to understand the canonical correlation. I mentioned the other time that we're actually gonna have two sets of variables, okay? And if I call, let me connect my iPad so that I will be, okay, let me do this. Now, if I have uh, one set of variable S, I said I'm gonna have another set of variable Y. Okay. X is gonna be X1 up to SP, and Y is gonna be Y1 up to YQ. We're gonna have like P numbers of X variables and Q numbers of Y variables. Okay. So if let's say for instance, I actually want to have a psychological measurement. Okay, if SSL include the locus of control, okay, let's say S include the locus of control, okay, and motivation, okay, motivation, okay, so locus of control, motivation, okay. and publish self concept. Okay, so self. I'm just assuming this example. Okay, self concept. Okay, like I said, locus of so the locus. Okay, locus of control. So I got three variables in X, so that I can probably call X1. Okay, X2. Okay, and S3. Okay, don't forget, when we're dealing with the principal component analysis and the factor analysis, we only have a set. But right now, we want to have two sets. So let me just call Y, um, you know, score. Maybe Y is a score of students. So maybe I'm going to say the math score, the score in maths. Okay, the score in maths. Okay, the score in science, the score in science. Okay, the score in science, and probably the score in reading. Okay, so if you take a look at this, I'm actually um going to say right now, okay, this is like Y1, this is like Y2, this is like Y3. Now, if you take a look at what I'm actually displaying now, I actually have a set of S, I have a set of Y, and of course, we actually want to use the idea of canonical correlation to reveal, okay, that the first canonical variant from the personality set is strongly related, okay, with the probably with the locus of control, motivation, and so on like that. So we actually want to have a situation, or we are we're going to construct a canonical correlation between the linear combination of this guy and the linear combination of that guy. Okay, and that's exactly what we mean. And of course, a strong correlation or relationship between personality profile may be characterized by high locus of control and motivation and overall academic performance. So now you understand what our intention is. Okay, two set of variables will be involved, and we actually want to have a way to derive the maximum relationship because we want to identify the combination of the two that will give us the maximum relationship. Okay, so let's go into the mathematical aspect of this and see how it's going to play out. Now, uh, I think I just explained the purpose. Okay, I gave you example of two set of variables. And then, of course, the canonical we connect the two set of variables, finding linear combination of variables that we maximize the correlation. And of course, the two purposes of canonical correlation also have to do with data reduction. But the data reduction here, we explain the covariation between two set of variables that we talk about using the smaller number of linear combination. Don't forget, the first set of variable, we're going to have a linear combination that has to do with the first set of variable. We're going to also have some set of linear combination that has to do with the second set of variable. And in a way, this perform a dimensionality reduction task. And of course, at the end of the day, we should be able to interpret, okay? We should be able to find, the resulting canonical variate that may be important, in explaining the whatever covariation that may exist between the set of variables. Okay, now I need you to pay attention. before moving forward because where we are right now is critical. But I want to start unfolding. I want to start showing you the mathematical aspect of this. Can somebody confirm again if you can if you can hear me clearly?
I can confirm.
Okay, thank you so much. Thank you for confirming that. Now, what we want to do uh right now is I want to go mathematical. Okay. I want you to see, like I said, two set of variables are going to be involved. Okay. This is going to be the first set of variable X. This is going to be the set of variable Y. Okay. Let me tell you this. There's so many examples that we can actually cite. Okay. You could have a situation where X represents some X measures and Y may represent the exercise measure, stuff like that. Now, when I have a vector of X like this, the mean exists. This is the mean. When I have a vector of Y, the mean also exists. And, for this guy, okay, give me 1 second. If I'm focusing on one set of variable, okay, there we're gonna have two parameter associated with that set of variable is gonna be the mean and the covariance structure. So this two now will be the parameter. Okay, we're gonna be the mean and the covariance structure of the first set of S. And I'm also gonna have for the second set of Y, they're gonna have the mean, they're also gonna have their covariance structure. But in a canonical correlation, of course, we actually want to consider both, the both set. Okay, want to consider both set. Okay, so if I let a particular variable z to represent that, okay, now the z following a normal distribution now is going to be, a combination of the two set of variables in such a way that if I want to now focus in on combining the two sets, so this guy now is combining the two sets you know follow a normal distribution. This is going to be the mean and this is going to be the covariance. Okay, I wanted to take note of that. We are combining the two sets now because to be able to figure out the canonical correlation, it is expected that we combine the two sets. Okay, so if you take a look at that, this is a general covariation where the diagonal here. Okay, if you take a look at the diagonal here, okay, the first one, each of them, they're going to be matrix on their own. Okay, this guy's gonna be a matrix, this guy's gonna be a matrix, that guy's gonna be a matrix. All of them, they're gonna be a matrix on their own. Okay. Now, from that, the next that I want to talk about is here, trying to tell you that the way you're gonna get this guy, okay, of course we've done that before, which is going to be the covariation, okay, the covariance between X and Y. I remember the other time, if I wanted to know, is there any relationship between members of this set and the members of that set? That's exactly what I mean. Because if that relationship exists, the canonical correlation is going to benefit from that. Now, I want to go into the combination right now. Let me tell you this. If I have a set X, okay, I want to derive, uh, linear combination based on set X, which is similar to what we did in principal component analysis, where we artificially fabricate a principal component that is a linear combination of the features. Okay, we're also going to do the same thing to the set of Y. Okay, for the set of Y, we actually our V, our V is a linear combination of the set of Y, while U is a linear combination of the set of X. Okay, now it's like we are having new variables right now that we have generated. Okay, the new variables is u and v, where u is a linear combination for this set of x, and y, v is a linear combination for the set of y. And of course, the a and b, they're going to be the constants. Okay, of course, in any linear combination, there's going to be some constant. So we're going to have constant of A for S. We're going to have a constant of B for Y. So we derive a new variable U and V. Okay. Now, the next that we want to do, the new variables that we have derived, the new variable, the U and V, okay, U is a linear combination of set X, and V is a linear combination of set Y. And what do we want to do? Uh, the correlation, we actually gonna look into correlation between U and V, looking into that. Okay, if I want to talk about correlation, okay, I need to be able to understand what is the variance of U, what is the variance of V, and what is the covariance of UV. Of course, that in the formula for correlation is the ratio of the covariance between variables to the square root of the product of the variance. And that is the reason why, we need to be able to derive the variance of U, the variance of V, the covariance of UV. Okay. And when I obtain the correlation for U and V, that will be called canonical correlation. So U and V will be called canonical variate. So you take a look at this guy now. The variance of U is going to be that. If you want to go by what we did before in the matrix algebra, and of course the variance of this guy is going to be this guy. Don't forget, B is a constant. A and B, they are constant. That's why you actually, when constant come out of the variance, it's going to be squared. Okay, and the way to write is squared, if I want to write, you remember in a conventional, classical statistics, if I have a variance of AS, okay, for instance, if I have a variance of AS, okay, if I have the variance of AS for classical, so I'm actually going to have a squared, right, variance, a squared variance of X, okay. If I want to write this in a matrix form, if I want to write this, A squared is going to be A transpose. I'm going to put A right here, and the variance of S is going to be this guy. Okay, you remember we've done all of that before. So that's exactly what we're saying here. Okay, we are indicating a subscript S to tell the world that that's a covariation around the variable S. Okay, and this is the covariance between the two canonical variates. Okay, now if I have that set up, I'm actually every other thing is gonna be so easy. Now I have this set up right now. Now the very first thing I'm going to do is I want to find the first pair of canonical variates. Why do I have U1, V1? Don't forget, in the case of principal component analysis, when I was focusing on a linear combination, don't forget, we normally have the first principal component, we have the second principal component, okay, and so on like that. Okay, so even here too, there's going to be a lot of linear, a lot of variate or canonical variate for that. We're going to have a V1, we're going to have a V2, and so on like that. And each of the V1 and the V2, they're actually going to be a linear combination of the set of Y. And of course, each of the U1, U2, and so on like that, each of them will be a linear combination of set of S. Now, if I take a U1 here and I take a V1 here, okay? Now that's what I mean here. That's what I mean by first pair of canonical variates. So if I actually want to obtain the first pair canonical variate right now, I should be ready to find the correlation between U and V. The correlation between U and V right now is actually going to be the ratio of this guy to that guy. And of course, don't forget the covariance, this guy. Okay, in that case, we depend on A1 and B1. Okay, and the variance of U also going to depend on A1, and that's going to then this is going to depend on B1. And what we actually want to do right now is, can we have a way to derive the first pair of canonical variates, okay, that maximize the correlation? We want to have a linear combination of that we maximize. Don't forget, we're seeking to maximize the correlation, just like our typical, synonymous with what we did in the principal component analysis. In the principal component analysis, the first principal component, we have the largest variance. Okay, we are seeking the same here. Okay, and when we're doing that, then we have condition. The condition is that the variance. The condition for the first one is that the variance of U1, okay, and the variance of the V1 has to be one unit variance. That's all we mean by unit variance. If I'm seeking the first canonical, first pair of canonical variate, okay, and of course, I said the remaining canonical variate maximizes the above, subject to having the unit variance and being uncorrelated. Now, let me tell you this. This is a general form of a principal component analysis. Uh, the reason why it's a general form is because of the fact that in principal component analysis, the first principal component has the largest variance, okay, and the second principal component, is the next in terms of the magnitude of the variance. So we are also seeking the same, for the canonical. So, we believe that the first pair of canonical, of course, we have the maximum, we are maximizing the variance, and of course, the remaining canonical maximizes the above variance subject to that, and they have to be uncorrelated. Of course, in the principal component analysis, any two principal components should be uncorrelated. Uncorrelated means they're going to have their covariance equal to zero. Okay, so that's exactly what I mean. Now, how do we go about computing canonical variates? When I say canonical variates, okay, the linear combination, okay, so I want to actually compute the canonical variate, okay, for UK, okay, and for VK. Don't forget, linear combination, okay, for set of S and combination for set of Y. Okay, so if I actually want to do that, okay, there's something I need you to see, okay, something I need you to see, okay. If I want to rewrite this guy, I can write this and S, okay. So the whole of this guy is K I'm talking about. So for the kth variate, okay, for the kth variate U, okay, this is what I'm going to, but I want to figure out A, I give me that. And what is the U? What, because this is trying to say U transpose. What is my U? My U is the eigenvector of this guy. U is the eigenvector of this guy. The same thing here. This guy, that's a BK. That's a BK, right? Okay. Now, this guy now, that BK now. So if I want to, before I can get the BK, I need to first get the VK. So which is the eigenvector of this guy? In this class, I've already walked you through how to figure out the eigenvector, okay? The eigenvector, okay, of a matrix, okay? And before you can get the eigenvector of a matrix, okay, you need to you need to fall first, like you find this guy, you find that guy, you find this guy, you obtain this guy, you obtain that guy. Then after obtaining that, you multiply all of this, and after multiplying all of this, then this guy is going to be a matrix. And now the eigenvector of this now is what we call the UK, and the eigenvector of that is what we actually call VK. So what we're trying to do here, you want to get the kth pair of canonical variate, okay? So that's what I mean. Okay, so if you take a look at, that's how, like I said, that's how you're gonna navigate that part. Okay, now the moment you have obtained the UK and the VK, we can look at the correlation between the two. So the correlation between the two is going to be called the Kate canonical correlation. So the Kate canonical correlation, of course, is going to be denoted as a Roy K. Okay, it's going to be denoted as a Roy K. And of course, there's something I also wanted to take note. Do you know that the square of this correlation is actually the eigenvalue of this? Okay. If you can go back to what we did on the you know eigenvalue decomposition, you're actually going to understand all of that, where we figure how we learn how to obtain the eigenvector and the eigenvalues. Okay, so of matrix, I told you from the one that the knowledge of matrix algebra is very crucial in this class. Okay, so there's that. Now, okay, now the next in the line, I want to talk about the covariance. We can have a situation where can we talk about, is there any relationship between the original and the canonical variables? When I say original, okay, I mean maybe X, some variable in the set of S, and they are canonical variables. The canonical, now this is what happened, okay? Uh, this is the original X and the original Y, right? So this guy and this guy are their canonical, okay? What we call the canonical variables. So can we have a way to investigate if there's a connection between the new variable that we form, okay, which is a canonical variable, and the old variable, okay? That's exactly what we mean. Now, let me tell you this. For set of S, okay, for set of S, we're actually going to have U1 up to UP canonical variate, okay, which is going to be the canonical variate from S. We're talking about so many, each linear combination that we derive, for X, U1 up to UP. Then, of course, V, the one we derive from set of Y, okay, and we know with the fact that P is less or equal to Q. Don't forget U, the numbers of linear combination that we derive, like number of principal components, okay, is P for S, and for Y is Q. And of course we we are interested in situation where P is going to be less or equal to Q. Okay. Now, if I want to look at the covariance, that's what I'm doing here. Okay, so right here now, if you take a look at what I'm doing here, can I look at the covariance between U and X? Don't forget this particular U here, okay, is canonical variate derived from S. The canonical variate derived from S and the original S. Is there any relationship? Don't forget that U, okay, the U is a linear combination of S, which is this guy, Okay, now right now, I want to find the covariance between A prime S and S. Okay, and this is the formula. This is what we're gonna have. It's gonna be A prime, okay, sigma S. Okay, because you're actually gonna have S and S. The covariance of S and S, the covariance of the same variable is the same thing as variance. And that's why you have this guy here. Now you want to do the same between U, the linear combination, okay, the canonical variate that you derive from X and the original Y. Okay, this is the formula for covariance. Okay, then for others as well. So take a look at that. So what we're doing here, can we have a way to investigate whether there's a relationship between the new set of variables we derive? Don't forget, which are the linear combination of the original features and the original feature itself. So that's what I mean here. Okay, now I'm actually moving. Now, the same way that we are looking into the covariance structure, we can also look into the correlation function structure. So here we are looking at the correlation between the new set of variables developed and the original. That's what we're doing here. And at the end of the day, of course, we end up getting this. Okay, so we are looking into relationship between the canonical variates, okay, the canonical variate and the original variables, okay? So that is what we just derive right now. Okay, so with the fact that the variance of the linear combination derived from S is going to be the same as the variance of the linear combination derived from Y, and they're all going to be equal to 1. Don't forget, I said the other time, the variance of each linear combination, whether you the one you derive from X or the one you derive from Y, has to be equal to 1, that we call the unit variance. And of course, we take a look at well, this is the you're gonna find that in the diagonal. Okay, this guy. Okay, you see having it's having this guy on that. It's gonna be the diagonal of this guy. Okay, so don't forget the covariance around S. The diagonal of the covariance around S is gonna be this guy that you need here. You can see where you can see the star, the one with the star, and the one for Y is that. So the diagonal. So if you want to figure out, you want to figure out the correlation, of course, they're just trying to tell you what you're actually going to use. You can see all of that, have that sign on them, and they're just trying to point it to how you can figure it out. Okay, so is summarizing variability right now. We've defined a linear combination for S and a linear combination for Y, and we are seeking to maximize the correlations between any two canonical variable. And of course, but let me tell you this, we're not explaining the difference that it has with the different that it has with the of principal component analysis is that it is not, take a look at that, it is not the same as maximizing the explained variance. In the case of principal component analysis, the idea behind deriving the set of principal components, we actually want to settle for few ones that can maximally explain the variance. So this is not the same as that. Okay. The only thing that we want to do here is we only want to maximize relationship between two set of linear combinations. Okay. That's our intention here. Okay. So here, and I say, if the first few pairs of canonical variables do nowhere explain the variability in that guy and that guy, then the interpretation becomes less clearer. Okay? So, in terms of explanation now, we are referring to the canonical variables. Okay, now you know, in the situ in the, I've been talking about population all this why. I also want to, what if we have our sample data? Okay, so if we have our sample data, okay, so I have two set of X, set of data, X and Y, set of X and set of Y. They follow normal distribution. Okay. And of course, this is going to be the mean. The mean for the set of S is going to be the mean for set of Y. And this is going to be the general covariance structure where this guy is going to be the covariance for the set of S, the covariance for the set of Y, and the covariance for the set of X and Y. So if you take a look at what I have here, if you take a look at what I have here, this is for the population. Okay, that's why this guy and these guys, they're gonna be called parameters. Okay, they're gonna be called parameters. Okay, so this is for the populations. But if I want to talk about sample, if I have a samples of data, okay, so I'm gonna be talking about estimate. You can see X bar, Y bar. X bar is the estimate of that, Y bar is the estimate of that, and I'm gonna be talking about sample covariance structure. Okay, so these are for the sample, these are for the population. Of course, if I have my data set, I'm actually gonna have a sample of data, and of course, I'm gonna be working on that. Okay, now, I'm gonna be walking you through the sample one. Okay, so here they're just trying to tell you how to figure out each of that we've done in this class. I'm actually gonna move. Now, this is what we've done before. Now we want to talk about with when we have sample data. Okay, when we have sample data. Okay, so the linear combination of X is V, the linear combination of Y is V. So the linear combination of X is U, the linear combination of Y is V. Then you can see in the sample, I'm actually going to be estimating. That's why you see a cap. You see a cap on the variance. You see a cap on the V, on the variance of V. You see a cap on the covariance. It means we are estimating. Okay. In the population one, it was this. So the population one I showed you the other time, this is the population one. This is the sample. So the only thing, this guy is going to replace that. Okay. So the same thing applicable to all of this. Okay. I think I've shown you the population one before, and what I'm going to be showing you now is going to be the one for the sample. Okay. And of course, you can see if I want to get a correlation, it's going to be estimate of the correlation. They're all going to have a cap on them. And of course, you can see this guy has changed. Okay. The covariance structure that we are using, we are telling the world when we are using S, it means the one for the sample. Okay. So don't forget, they're all going to have the variance of U1, the variance of V1, and all of that, variance of U2, the variance of V2, all going to have unit variance, just like what I said before. Okay, now how do you calculate canonical variate? When you have a sample data, I show you the population one the other time. Okay, the only difference you're actually gonna see is that this is having a cap, and that is having a cap to show it's an estimate. And of course, the A is having a cap, the B is having a cap, and don't forget, my A cap is all of this. Okay, so if I want to get if I want to estimate this guy, I need to be able to, have a way to compute this. And of course, the estimate of this is actually what I mentioned the other time. That's going to be the eigenvector. It's going to be eigenvector of that. And of course, here is going to be the eigenvector of that. So we are working with a sample right now. I think I show you the population one the other time. Okay. Now, uh, and of course, the moment you are able to estimate, what your U and what your V, your U and V is, we can begin to look at the correlation between them. Also, because the canonical variates were estimated, of course, we also going to estimate the correlation between them that we call the canonical correlation. Okay, so it's going to be this guy. And of course, just like what I said the other time. So just like what I said the other time, okay, the square of the correlation is the eigenvalue, okay, eigenvalue of this guy. Okay, the square of the correlation is actually the eigenvalue. So if you get your eigenvalue for this one, if you square that, you have your canonical your canonical correlation. Okay. So whichever way you want to go, maybe you want to go finding the eigenvalue of this one and you square that. We find the eigenvalue of this one, find the eigenvalue for this one, that will give you a square of correlation. And by the time you find the square roots of the squared, it's going to give you this guy. So this is the canonical that we talk about. So if you want to go by finding the eigenvalue of this guy, what the eigenvalue of this guy is going to give you is the square of that. So to be able to get it, find the square root. And of course, if you want to go by eigenvector, okay, eigenvector will give you the value directly. So if I get the eigenvector, the eigenvector is always going to give me it's going to give me the eigenvector. It's going to give me just this guy, okay, and this guy. Then I will now need to multiply by all of this. So going by eigenvector approach may take forever, but eigenvalue approach is easy. I'm going to tell you why eigenvalue approach is easy. So the moment you get the eigenvalue of this guy, the eigenvalue of that guy is rho squared. And if I find the square root of that, I will get my canonical correlation. But if you want to go by eigenvector, if you find the eigenvector of this guy, you still need to multiply by this and this to be before you can get this, before you can get that, and you still need to go all the way to find the correlation. But that will be super easy when you find the eigenvalue for this guy. Now we can also, the other time I'll show you that we can look at the covariance. Is there any relationship between the original features in X and Y, okay, with the canonical variables? Okay, I show you the population the other time. So, which is what we're doing here, What we're doing here, we are estimating the covariance, okay, because we have the sample data, the covariance between the canonical variate derived from X and X, okay, this is the formula, okay. Then for the one derived from S and original Y, the one derived from Y and original S, the one derived from Y and original Y. So these are the estimated covariances. Okay, the moment we have the estimated covariances, we can we can have the estimated correlation. So the estimated correlation is actually going to be this. And of course, you may be wondering, how are you going to find, you can see on S, you see that sign. So it's actually the diagonal of SS. So that's the diagonal of that. Okay, so take note. Okay, so we want to talk about the covariance matrix implied by CCA for S. Now, let me tell you this. Um, Statistically speaking, if I look at the estimated covariance, okay, for the you know the canonical variates derived from S, okay. If I look into that, it should give me identity, okay. By statistical properties, it should lead into uh, identity, okay. I just wanted to take note of that. Now, we can actually, using the fact that that guy is an identity, okay? Now, using the fact that it's an identity, okay? If I decide to multiply out by the inverse of this and this, if you take a look at what I have now, the inverse of that and the inverse of the transpose of that. If you see what I have in the middle, what I have in the middle is identity. I'm only going to have this guy and this guy. So that's why you have this guy. Okay. And of course, that's if you bring that together, this is what I'm saying. And I'm using the fact that this is equal to this. Then from here, if this is equal to this, and I introduce this guy, I pre-multiply this by this, and I post multiply by this. Now, let us now simplify. You want to know what is going to come out from here now. Want to simplify that. Please pay attention. We want to simplify this guy. Now, in simplifying this guy, you're actually going to see that using the fact that this equal to this, okay? If this become my identity, I'm only going to have this guy. And if I have this guy, of course, you know, if you, the inverse of a transpose is the transpose of an inverse. You can see here, this is inverse of a transpose. Then it's the same thing as the transpose of an inverse. And automatically, that will become our SS. Okay, that is going to become our SS. Okay, now, and in scalar form, it is that guy. We can do the same thing to Y. Okay, okay, you can do the same thing to the one derived from Y. Okay, it's also going to be an identity. So by the time you pre-multiply and post-multiply, by this guy, also going to resolve into that. Okay, now this is the covariance matrix implied by canonical correlation, for X and Y. The estimate that I talk about, this is talking about the estimate of covariance between the two different canonical variates. I show you this formula the other time. So this is the way it is in the matrix form. Okay, that is the way it is in the matrix form. And of course, we can actually rewrite that as what you have here as the estimate. Okay, so don't forget, why is the covariance equal to the correlation? Because they're actually going to have a unit variance. They're going to have a unit variance. And that is the reason why, standardizing doesn't have effect in canonical correlation. Okay? Because in canonical correlation, the covariance and the correlation, they're going to be the same. Okay, and that's why you see, if I call this on an estimate of the covariance, which is equal to, so the estimate of the covariance is the same thing as the estimate of correlation in canonical analysis. Okay, which is what we're trying to say here. If you take a look at that, okay, we actually derive that, okay, that guy is equal to this guy, right? And if it's equal to that guy, so I can equate this guy equal to that, which is what I'm having here. Okay. Now, if that is what I'm having here, if I now, if you take a look at from here now, from here now, okay, you're actually going to see that that guy is this guy here, right? So what do you think I'm doing? I pre-multiply by the inverse of the transpose of that and post-multiply by the inverse of that. So when I simplify that, I'm actually going to have this, okay? So having this now, okay. And don't forget the other time I said the inverse of the transpose is the transpose of the inverse. So this guy will give me an expression for this. Okay. So you can take a look at that. Okay. Let me see, what do I have left? Okay, so we also talk about I think I'm gonna stop here. I'm gonna start from the CCA error of approximation, matrices in class tomorrow. And from there, I'm gonna talk about how do we investigate if you know, a canonical that we're seeking is a what, why. So we have a statistical test. I'm gonna walk you through all of that tomorrow. I'm gonna tell you, um, you know, the distribution that we can actually use for the test. And after that, tomorrow, then I'm gonna walk you through example. Okay? Is there, so I'm gonna have the rest of them reserved for tomorrow. Is there any question before I go today? Is there any question? Okay, so in the absence of question, uh, make sure you all stay safe. Okay, I'm gonna meet you in class. Gonna see you in class tomorrow. Bye for now, everyone.